Hello. So I didn't get through all of Chapter 5 today in class, so this is the part where I'm going to finish up talking about Chapter 5. So just to review a little bit about what we covered in class so far this semester. We went over constitutional isomers. Constitutional isomers were compounds that had the same molecular formula, but they were connected in different ways. Now, stereoisomers had the same molecular formula and they're connected in the same way, but they differ in the way they're arranged in space. So the three-dimensional orientation is different. And so what we've seen so far is we could have enantiomers. So enantiomers are non-superimposable mirror images. So they're mirror images of one another, but you cannot superimpose them. Diastereomers, they're connected the same way, you cannot superimpose them, and they're not mirror images. Cis and trans isomers would be an example of diastereomers. Let's look at a problem from your textbook. So if we look at these two problems, it says, what kinds of isomers are the following pairs? So here I have 5-chloro-2-hexene. So hexene, 6 carbons, 2-chloro-2-hexene, 1, 2, and 5-chloro, 1, 2, 3, 4, 5, 5-chloro. You can put a wedge or a dash to make it S. And then I have chlorocyclohexane. So I'll go ahead and make the S one here just as ready to review RNS configuration. So I'm going to make this a dash and see if I drew out the right configuration. So look at what's attached to your chiral center. Your chiral center, remember, is a carbon that has 4 different groups attached to it. So attached to this carbon I have a chlorine, carbon, carbon, then a hydrogen going back. So my chlorines, my highest priority. Next I have another carbon, no other carbons here. So this would be 2, this would be 3. And so that is clockwise configuration. So what I actually drew was the R. So what I could do to draw the S in would be just to make the chlorine R dash. That'll invert the configuration, so I'll have my S configuration. Regardless, you can see that these two compounds have the same formula. Okay. They both have the formula C6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. C6H11Cl. So both of them will have that formula. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. But they're connected in different ways. So that means they are constitutional isomers. Now the next one says 2R, 3R dibromopentane and 2S, 3R dibromopentane. So they're both dibromopentane, so they're connected in the exact same way. So they differ in the way they're arranged in space. So if I compare them, I've got 2R here, here I have 2S, so that's opposite configuration. Here I have 3R and 3R, so that's the same configuration. So when you have an opposite at one stereocenter and the same at another, that makes it a diastereomer. Now on Blackboard, you also have some supplemental homework where you give them some different molecules, and and you have to tell whether they're enantiomers, diastereomers, or identical. For those, it's easiest to just go in and see if they're superimposable. If they're superimposable, they're identical. Check to see if they're a mirror image. If they're a mirror image and they're not superimposable, they're an enantiomer. If they're not a mirror image, not superimposable, but they're still connecting the same way, they're a diastereomer. But if you're given the R and S configuration, it makes it easy. Remember, enantiomers are opposite at all chiral centers. Identical would be the same at all chiral centers. If they're the same at some, opposite at others, it's diastereomer. Look at what's known as a racemic mixture. So we'll see this a lot of times in chemical reactions. So a racemic mixture is a 50-50 mixture of enantiomers. And it's optically inactive because remember, enantiomers have all these physical properties that are the same, but they differ in the direction they rotate plane polarized light. So say you have an R enantiomer of one compound that rotates at plus 15 degrees. The S enantiomer will rotate at minus 15 degrees. And so if you have a 50-50 mixture of both, they rotate to the same extent but in opposite directions, they cancel each other out. So that's what, in substance, that optical rotation cancel each other out. It does not rotate plane polarized light, and so it's optically inactive. So that's what's known as a racemic mixture. Separation of enantiomers is difficult because they have the same physical properties. And so in lab so far, we've been separating compounds. We've separated compounds based on differences in boiling points. We use distillation. We've separated some compounds based on differences in solubilities using extraction. Later on in the semester, we'll separate compounds based on differences in polarity using thin layer chromatography. But with enantiomers, they have all the same physical properties, so it makes it very difficult to separate them. So the most common method for separating enantiomers is to use what's known as a chiral resolving agent. So let's look at an example of that. So say I have a mixture of enantiomers. I have my R enantiomer. That's my S enantiomer. They're mixed together. I react that with what's known as a chiral resolving agent. So it's some kind of a compound that reacts with each of my enantiomers, okay, but it's chiral itself. So now it reacts with the R enantiomer, so I have two chiral centers. They're both R, then it reacts with the S, making a compound that would have two chiral centers, one being S and one being R. Now the relationship between those two would be diastereomers, because same configuration here, opposite configuration here. So now that I have diastereomers, diastereomers have different physical properties, and so they can be separated. So that's one way to separate a mixture of enantiomers. Another type of projection we'll be looking at is what's known as a Fischer projection. Fischer projection of tetrahedral carbonate is represented by two cross lines, like that. The horizontal lines represents bonds coming out of the plane. The vertical lines represents bonds going back into the plane. two cross lines. That's the same thing as writing. Okay, so horizontal lines represents bonds coming out of the plane. So that would be a wedge. So I have an OH attached there. This would be a wedge. I have my hydrogen. Vertical lines would be going back into the plane. So that's what Fisher projection represents, but it's just shown as a cross line. So if I did the RNS configuration of this, here's my chiral center. First atom, carbon, oxygen, carbon, hydrogen. So that's my highest priority. Next atom, oxygen, so this would be 2. This would be 3. So 1 to 2 to 3. And so that is a counterclockwise rotation, but which is normally S. But my H is coming out. So you have to remember what Fisher projection represents and know that this horizontal line means it's coming out. So I have to say opposite. So it's normally S, but I'm looking at it from the wrong side. So that's actually an R configuration. This says convert the following tetrahedral representation of R2-butanol into a Fisher projection. So it's going to be a cross line. So what I'm going to do is just take it and rotate it over. So if I'm just taking it and rotating it, these two will remain the same. Now when I rotate it, my OH is coming out like this. And when I rotate it, it's still going to be going out, but I'm just rotating like this. So it's going to be out there on the right side. So I can do RNS configuration, check my work, make sure that's the correct Fisher projection for that. So it says R2-butanol, I can check that and say, okay, 1, 2, 3. Yeah, that's clockwise, my H is going back. That's R2-butanol. I'll look at this one. Again, sound my priorities. This one, I get a counterclockwise rotation, which is normally S, but remember, it's a Fisher projection, H coming out, so it's R. So since they're both R, they're the exact same thing. So that is a Fisher projection for that molecule. There's other Fisher projections, the other Fisher projections showing R2-butanol, but that's one of them. We got a couple more concepts in this chapter now. So this is the concept of prochirality. So a molecule is said to be prochiral if it can be converted from achiral to chiral in a single chemical step. So this would be an example. So in this reaction, I basically see that I'm adding hydrogens to my pi bond there. And so here, no chiral centers. After this reaction is complete, I see a chiral center. So single chemical step makes a chiral center, so this molecule is said to be prochiral. The enantiomer that is produced depends on which phase of the substrate undergoes reaction. To distinguish between phases, Re and C are used, which are similar to R and S designation. So look at that example. So I'm assigning priorities here. So 1, 2, and 3. Okay. So I go 1 to 2 to 3. And so that is clockwise. And so this is the direction I'm looking at. I'm looking at from this side. And so Re and C are similar to R and S designations. So I'm looking at it, and I look that it goes clockwise from this side. So this is what's known, this front side that I'm looking at here would be known as the Re face. So that means the opposite side, if I was on the opposite side, would be the C face. Okay, so something, the hydrogen coming in attaching from this side would be addition to the Re face. Going from the opposite side of the smart board would be the C face. An sp3 hybridized atom is said to be a pro-chiral center if by changing one of its attached groups it becomes a chiral center. So here I've taken off a hydrogen, added a halogen, so again, chiral center, this carbon, 4 different groups attached. Here not a chiral center, but since one of these, change one of these attached groups, made a chiral center, this would be an example of a pro-chiral center. Of the two identical atoms in the original compound, the atoms whose replacement leads to an R chiral center is said to be a pro-R, and the atoms whose replacement leads to an S chiral center is said to be pro-S. So to do this, you look at like when you replace it, you look at it as just being just a step above hydrogen, so like a deuterium atom. Okay, so it's below all other atoms, just above hydrogen in terms of assigning priorities. So let's go ahead and look at some problems. This. Says identify the indicated hydrogens in the following molecules as pro-R or pro-S. So if I'm looking at this one, okay, so I'm changing that one, so just to be a step above hydrogen. So this would be 4, this would be 3. So look at my other one, so oxygen, carbon, so this would be 1 and 2. So then I say, okay, that would give me a 1, 2 to 3. So that is counterclockwise, which is S. So that means that hydrogen is a pro-S, and the other one must be a pro-R then. So again, I'm looking at this one, so I'm going to make this one my 3. Okay, so their hydrogen's a 4. first atom, carbon, carbon, next atom, 3 carbons, nitrogen, carbon. So there's a nitrogen here, so that makes that the top priority. So now I go 1 to 2 to 3. So that's clockwise. So that means this one is pro R. That one must be pro S. Look at one, looking at the different faces. So it says the lactic acid that built up in tired muscles is formed from pyruvate. If the reaction takes place with addition of the hydrogen to the reface of pyruvate, what is the stereochemistry of the product? So I'm adding hydrogens here. So I want to see, okay, what face am I looking at from this side? So oxygen, carbon, carbon. So this would be 1. Other oxygens here, so that would be 2. This would be 3. So 1 to 2 to 3. And so that means that this is the reface because that's R, that's clockwise. So my hydrogen must be adding from this side, so I'm going to go over here and draw that. So I have my CH3, my CO2 minus. So hydrogen is adding from this side. So it's adding from this side, it's going to be coming out of the plane. And then I have my OH group. So now it says, what is the stereochemistry of the product? So the reface and C-face has to do with beforehand. So it doesn't matter what product it leads to. So you can have addition to the reface that leads to an S product or an R product. So let's determine the stereochemistry of this one. So highest priority, OH group. Next one will be the CO2 minus, then my CH3. So 1 to 2 to 3. So that is clockwise, but my H is coming out, so that's the opposite. So that would be an S product. Last thing we're going to look at is chirality in nature. So although the different enantiomers of a chiral molecule have the same physical properties, they usually have different biological properties. So one biological property that we're actually going to see in lab is odor. And so compounds that are enantiomers of one another will have different smells. But another more dramatic difference would be in pharmaceuticals. And so, like, I gave an example of enantiomers being like your hands. So they're mirror images of one another, but you can't superimpose them. Or in your body, you have these drug receptor sites that are like a glove. And so, like, say it's a right-handed glove, the molecule comes in and fits into that drug receptor site. The other enantiomer will not fit to that drug receptor site. And so it's only one of the stereoisomers that's actually active in your body. So let's look at your textbook for some further examples of this. So here's one that I gave. So I said the odor differs, and so here you have 2 enantiomers, non-superimposable mirror images, where the plus enantiomer has the odor of oranges and lemons, the minus enantiomer has the odor of pine trees. So just enantiomers, but they smell differently. Here's another example. Look at this example. Fluoxetine, which is sold under the trade name Prozac. Racemic fluoxetine is an extraordinarily effective antidepressant but has no activity against a migraine. However, the pure S enantiomer works remarkably well in preventing a migraine. Another example is ibuprofen. So ibuprofen is a chiral molecule. If you read this here, it has one chiral center. It's sold commercially under trade names as Advil, Nuprin, Motrin, and it's sold as a 50-50 mixture of R and S. It turns out, though, however, that only the S enantiomer is active. Okay, the R enantiomer is inactive, although it's slowly converting your body to the active form. So only the S enantiomer is active, but if you look at this, it's sold as a racemic mixture, so you have both the R and S enantiomer in there. But if you had the pure S enantiomer, it takes effect on the body in 12 minutes. Racemic mixture takes about 38 minutes, so it really slows the rate at which it has an effect on your body. And so, in that case, okay, why if the S enantiomer works so much better, why is it sold as a racemic mixture? And that has to do with the production of it. When you make it, it's really hard to make just a pure S enantiomer. And so if you then separate out the S enantiomer from the racemic mixture, it adds to the cost. And so they're just able to sell it cheaper by selling the racemic mixture. But that's it for chapter 5, talking about chiral molecules. And so we go on to chapter 6 now, and I'll see you later. Bye.